funky guitar blues.
Hey everybody, thanks for joining again for another week office hours on DynamoDB. My name is Rick Houlihan. I've been doing this every week for a couple of weeks. Most of you guys know me by now, and hopefully we've got some new folks and watching the stream as well. We got a pretty good session today for you. It's going to get deep into the mechanics of DynamoDB. We're really going to look at GSI replication lag and what it means. How do you minimize that lag and what it actually really looks like? I mean, I hear a lot of customers complain about, or not necessarily complain, but the concern that a lot of customers have, and sometimes complaints are that the consistency of GSIs, right? They're eventually consistent, and so when people hear eventually consistent, I mean, developers, they go nuts, right? We always, oh, my data's got to be consistent, and when you get into the mechanics of what does that really mean, and as far as the impact on your application, and what it really comes down to is this thing that we always kind of call or refer to as replication lag. Like, how long does it take from the time that the data updates on the table to the time that it updates, across the system, and various systems operate in various modes and various levels of consistency, and DynamoDB in general is a strongly consistent database. It has read after write consistency on the table. If I write data onto the table and I read back and I specify that I want a strongly consistent read, then it will read from a master node which accepts all writes, and therefore guaranteeing that whatever data you get back from that request is going to be consistent. But that really only applies to the table, and it also applies to LSIs, which are actually created and maintained on the same exact storage node. As if you're familiar with DynamoDB indexing, you have a local secondary index which allows you to kind of resort data, and you have a global secondary index that allows you to regroup data. So the former is consistent with the table, strongly consistent. When I write to the table, the updates to the table and the GSI occur at the same time. But the GSI is a little different beast. It's kind of its own table. You allocate capacity for that all by itself. The LSI consumes capacity from the table. A lot of people think that means that the LSIs are free, but that's a common misconception in DynamoDB. It just means that you need to increase the capacity pool that you have allocated to the table to account for the fact that you have these LSIs. The data still needs to be regrouped and stored in a different container. But in GSIs, it might as well be a different table. It's just a table that we maintain, and there's a contract that is actually maintained between the table and every single index in the system, right? And that contract is that when a table write is accepted, that update to the table will propagate to the GSI, and it will be consistent eventually. And today we're going to explore a lot about what that really means. But the fundamental issue that it comes down to is that GSI replication is really, really fast, and as long as the table is properly configured. So let's get a little bit into this. One of the discussions I had recently with one of the professional services the consultants that I work with was around a large loan processor, and the loan processor is actually an aggregator, and they aggregate millions of loan applications for various types of loans for consumers across industries, mortgage loans, consumer loans, retail loans, and every day they have a process of submitting loan applications of various types by various sellers, and as you can imagine, we're talking about tens of thousands of records, hundreds of thousands of records that need to be processed very quickly, and so one of the things we're going to do is just kind of walk through what that schema would quickly look like, and then we're going to talk through some of the use cases around these aggregations and what kind of pressure they put on the system. Because one of the processing requirements that this loan processor had was that updates need to be initially, when we talk to them, strongly consistent, right? And we'll demonstrate how we kind of showed them that the level of consistency that's maintained is something that we can accommodate within the application that they had. So, and really that was about making them comfortable with replication lag. So that's kind of where a lot of this came out of. So anyways, long story short, let's pop into our Nosql Workbench, which we always like to take a look at here. Make sure I might have that sized incorrectly. And this was one of our older schemas that, if you might recall from a couple weeks ago, we looked at a stock trading platform, but we're going to go ahead and create a new schema, for today's discussion. And so we'll call this one loan processing. And so in this application, we had, it was fairly straightforward, right? Customers had loan applications, applications had, processing requirements, and one of those was that had to be met before they could be submitted, right? So, and the reason I kind of want to show you this is twofold. There's an interesting way that we were able to accommodate their query requirements, but there's also obviously an aggregation issue because eventually they want to get all the loans that need to be submitted from a given seller. And so let's go ahead and just create our table to start containing the data. Oops, that's the data table. As you all know by now, I should probably just have one of these things created automatically so we don't have to walk through this every week, but this is, I like to create these generic tables. We have the type attribute. We're going to have a GSI PK. We're going to have a GSI SK. And there might be a data map that we're going to have some stuff in. So let's go ahead and put that in there. We're going to create the global secondary index right now, which is going to be our GSI1. It's going to be partitioned on GSI PK. Sorted on GSI SK, and we're going to go ahead and add that, and then we can go ahead and save the table. Oops, I don't want to add, that's right, I didn't need to add another one, I just want to save that definition as is. All right, so now we have a data table, we have one GSI, and let's go ahead and again start populating items to see what things actually look like here. Now, loans were grouped by customer, but they didn't really have a customer item. They basically needed to get loan applications for a given customer ID. So we did create customer partitions on the table, and so that was kind of our primary grouping because that was one of their most frequent access patterns was to look at what loans a customer might have. So we're going to say customer ID is our primary partition key, and we're going to have some sort of a loan date application for the date, or some sort of a loan ID. We could even just do loan ID here. They didn't really, in their particular application, dates were not relevant because it was all about active applications. What was the status of the application? Did it need to be submitted? Was it in process? And their batch operations basically daily were get me all the applications that need to be submitted for a given seller, right? Which we actually forgot to add that attribute. Or did we? We can use the GSI PK as our seller ID because that's really what we're going to be aggregating on. And this is, let's say, a home loan. This might be car. And this could be loan ID 1. And maybe this could be seller ID 1, different aggregation. And so for the sort keys on these loans, this is really, do we need to, yes, that's where we needed to get the date sort because at times they needed to pull out all the loans in a given state by date range. I knew we had that somewhere. I don't know what today's date is. What is today's date? It is the 21st. There we go. Let's just call it 8/21. And I'm sure there'd be a time on there as well. And so we're just going to create some empty data maps here for these objects. And so now when we save these objects, I can look at that aggregate view. I can see that I'm grouped on the table by customer ID. I can get all my loans that are in process by customer ID. If I go back to my GSI, I can get my loans by seller ID. And this works great as long as I don't have a large number of loans, right? When I start to increase the number of customers, I start to increase the number of loans by seller, then the key pressure on this GSI starts to become extreme, right? So, if we can only support about 1,000 writes per second on a GSI partition, and if we need to aggregate faster than that, then what we're telling people to do is more or less spread that load out horizontally, right? Shard it. So how do we shard it? When we're going to add some salted keys, so to speak, to our GSI attributes. And to do that, we're basically going to select a value, some random value between 0 and n, which is going to be indicative of the rate that we're going to want to aggregate these items, right? So, let's say I'm inserting 1,000 items per seller per second, then I don't necessarily, then I can aggregate on the seller ID. But if I'm aggregating 10,000, per seller per second, then maybe what I want to do is start to look at increasing the shard space or the key space for this seller by adding a 0 to n or 0 to 9 value to the end of my seller ID, right? So now what I can do is say, okay, if I ingest records at a high rate, then I should be able to increase the throughput of a given seller on the GSI by adding a number of logical partitions to be able to spread that load across. Now all I need to worry about is making sure that I have enough storage nodes on my table, and that's all about provision throughput, right? We know for every 1,000 WCUs we provision on the table, I'm going to get a storage node. For every 3,000 RCUs I provision on the table, I get a storage node. So you can kind of look at, what was the maximum throughput this table's ever been provisioned to, and get some idea, roughly, of how many storage nodes you have. That's not really true. I mean, when you start to increase capacity beyond your previous limits, then it causes like table splits, which actually double the number of storage partitions. But regardless, it's safe enough to consider your throughput provisioning levels as indicative of how many partitions you have when you're designing your schema. Because really what we're looking to do is, I mean, the worst thing it could be is I have more partitions than I think if I go into production and I start messing with my provision throughput levels. But if I know that when I deployed this table, I deployed it at 150,000 WCUs, then it's going to have 150 partitions at least. Now maybe if I had some auto scaling algorithm that caused it to increase beyond that 150,000, I might end up with a larger number of partitions than I expect, but my calculations aren't going to be wrong when I start looking at sharding in my GSIs, right? It's really important to understand what is the velocity of the data, what is the size of the data. In this case, what we're really trying to do is pull out loans that need to be processed, right? So loans that need to be processed are have a couple of conditions in their data that are indicative of whether they need to be processed, right? So, one of the things that they have is complete but not not submitted. Those are two conditions that indicated whether or not a loan should be processed. The others are, loans that have been submitted, but they've been approved for resubmission, right? So there's been maybe some conditional criteria that need to be satisfied. And, if that condition has been satisfied, then they want to go ahead and resubmit the loan application. So there was, what was interesting about this is that the consultant who initially went in there and looked at the database to determine how to figure out which loans should be submitted was running multiple queries using different criteria and creating multiple GSIs to pull out loans that match one condition, loans that match another condition, and then merging those result sets in the application layer, right? So one of the things we did to kind of fix that problem was to say, hey, what you really need to know are the loans that need to be submitted. And there's some logic to determine whether the loan needs to be submitted or not. And so what we're actually going to do is we're going to tag your loans with a GSI keys only when they meet those conditions, right? So when I actually update the loan, I can check the loan values, and if the loan values match the submittable condition requirements, then add these keys. And if I don't have those conditions met when I make an update, then leave these keys off the items. And so this way now it doesn't matter how many conditions that I'm going to be actually indexing on. I can just create that logic in the application layer when I make the insert or make the update to the existing item to set these keys if these values all match these criteria. And this gives me the ability now to just query the GSI for all loans that need to be submitted. I don't need to know why they need to be submitted. I just need to know that they do need to be submitted, right? So that gives us a single attribute that I can look at and say, let's index it or not, right? And so that was an interesting aspect. So let's see what that actually looked like in the in the schema. What was really one of the things that got us here also was the fact that these loan items were very large. But the process that needed to know that the loans were going to be approved was actually I didn't really have to go look at the loan objects. I wanted to find all the loans that needed to be approved, and I could go get those items, right? And so what we actually ended up indexing was the approvals, not the loans. And so let's take a quick look at what that might look like if I edit this data a little bit. And let's assume that this is loan ID, and it's actually an approval record. It's not actually the loan. And that doesn't really carry any data. Well, let's go ahead and just create new items, right? Why do I need to update our existing items? So here's our loan item and our home loan item, and we're going to add approvals. And so these, we're just going to take these indexed attributes completely off the loans, because I don't really want these to sit on the GSI. These are big. These things were 75 kilobytes a piece on average. And so what we really want is to index approvals so that we can very quickly understand what loans should be approved. So I can go ahead and say these guys all show up in the same customers partition, because when I select by customer ID, I'm going to get all the loans, whatever approvals exist on any loans. And this could be a submission approvals. These two items are basically submission approvals for loan ID 1. And this is an approval. And this is an approval. And now my GSI PK is going to be seller ID. And I'm going to go with my 2020 date of today, 21. And so what we've done now is kind of vertically partition those items, right? Instead of having the approval attributes associated to the loan items, and I can actually go ahead and create a bunch of little approval items. And what makes this nice is that I don't necessarily need to update the items here when they need to be approved if there's some secondary process that needs to fire the approval. This was part of their deal, was that loans could get into a state where they were ready to be approved, but it was another system that actually approved the loan. And so having to tag these items meant that I had to write that item. That's 75 kilobyte right back to the table. That's 75 WCUs. If the process that runs the approval is asynchronous, then I can simply go ahead and inject the approval by creating a small item on the partition that's a 1 WC write. Okay, and then that item is what propagates to the GSI. Now I could certainly just use projections to keep the data off the GSI and keep those items small as well. But that table write was what was costing the customer, and by splitting this across two items on the table into the same partition, now when you look at the aggregate view, oops, oh, I lost the items I just updated. I hate that. That's a little gotcha in here. If you leave the editor before you save your items, then you're going to lose your items. So I've got to quickly put these guys back in here. Sorry. That was my mistake. So hopefully you guys caught that, what I described there. So what happens here is these loans, they can be approved, but based on the loan, criteria update. They can be approved based on an exterior process, depending on the type of the loan, and having to update these loan items, right? It's one thing if I'm already in the loan item and changing, the information that's in this data block, and I have to make that right anyways. But it's another thing entirely if the approvals are coming in from a third-party process, approval for submission, and I have to go ahead and update this item and pay 75 WCUs just to update you're good to go. So by inserting these items into the partitions as approval items, we were able to offload those updates to the loans themselves. And if the update to the loan created an approval to send, then we just create the item as well, right? So it accommodated all processes. It minimized the access pattern there. So Again, we go to the GSI, we can see we're sharded across the seller by date range. We can now go get all the loans for a given seller that are approved to send. But it doesn't matter what criteria that are used to approve to send. We don't have to create multiple indexes. We can create one index. So this is a really good application for demonstrating how you might need to shard the data. So let's take a quick look at what it looks like in the system when we go to set up the database for sharding. By the way, today's code, for the first time, I actually have a repo online. It's a Git repo that I'm committing the code to. The code I'm using today is going to is available in Git under my Git name Houlihan, and I only have one repo. It's the DynamoDB office hours repo. So if you go in there, there's no README right now, so I'll add a README. The table loader utility is really the evolution of the tool that I've been using for the last couple of weeks to populate tables, do global tables demos, all this kind of stuff. I've been munging some code in there in the load item methods. You'll see those in there. Today's items are relatively simple structures. I'm going to go ahead and publish all of the Lambda scripts that I've been using for my statistics and updating and things like that as well in another folder inside of this repo. So it'll all be available for you, and hopefully I'll get some time to put a README together. But the tool itself actually does have pretty good self-described. It's a usage mechanism in there. It tells you what the options are and how to use the tool. Anyways, table is pretty straightforward. We've got the same table that we used last week, our data table. I've got a single GSI. I've gone ahead and provisioned these guys out to 40,000, 150,000 read capacity. Hang on one second here. And again, I do that because I like to get a large number of partitions available on both the index and the table. After this, you can flip these back to on demand. You'll still have some really nice performance. One of the things about the tests that I do, these tables sit idle for long periods of time. When you do that, sometimes the replication infrastructure behind, different things can happen. Leaders step down, leaders step up on the storage nodes. When you're not necessarily going to be updated, the replication agents don't necessarily update until items actually appear in the queues. So if you let your table sit there cold for a long time, then there are times when your replication lag can increase, right? So one way to keep your tables hot is to warm them, right? To have a synthetic transaction that executes every 60 seconds or so, and just keeps those agents and those replication agents hot and active. It doesn't happen a lot, but it was something that I noticed, and I actually had to work with the team to track down. I was like, what is this weird inconsistency I'm seeing? And they were like, how did you even find this? And it turns out that we don't have a lot of tables that just sit idle forever at high capacity, but I do. So because I do these oddball tests. So I think that's probably new guidance I'm going to be giving to customers is, let's create a synthetic transaction across your tables, especially if you see like spiky workloads with long periods of idle activity, or zero activity is really what it comes down to, which is what I was seeing. Then you can come into this state where, and it's not like terrible, but it does add a second or two, and that's frustrating when you're trying to talk about tight eventual consistency and replication lag sub 1 second, sub 10 milliseconds, right? I mean, you don't want to see these periods where all of a sudden you get these situations where replication lag can increase. So again, to make sure your lag is always going to be as low as possible, then run that. Make sure there's a transaction running on that table regularly. It doesn't have to be high volume. Just make sure those agents are aware of where all your leaders are on your storage nodes. That's what it all comes down to. And that can happen on tables like this, where I've got really high capacity, 150,000 WCUs, 40,000 RCUs. I mean, I've got 160 partitions out there. That can, and each one of those partitions is three-way replicated. So that's 480 storage nodes, right? So one of those things stepping down and secondary stepping up because we had to do some sort of control plane operation. That's not going to be something that never happens. And again, that's something that I did find. So interesting how as you go through these investigations, you start to learn even more about the system that you're working with. I mean, I've been working DynamoDB for 6 years, and this investigation was interesting because it took me down into the guts of how this thing actually works. So again, that's what we're going to be showing you is it here. Let's go ahead and switch out to my console view. So this is again my node that's sitting up there in AWS, and we're going to just kind of take a quick look at first we'll take a quick look at the table utility that I'm using. This is the code that's published up on GitHub, and it's pretty straightforward. If you has a usage for all the parameters, how many items are we going to insert on the table? That is a required parameter. The number of index partitions. In this case, this tool is built to shard an index, right? We can build tools to shard the table too. You can actually use this exact same tool to shard the table. But what we're really doing here on this particular test is we're saying, I want some number of index partitions, and we're doing this to demonstrate, what happens when I have, small number of partitions, large number of partitions, various item collections. We can take a look at what that replication lag looks like. What is the table name we're hitting? Those are the 3 required parameters. Size of items in bytes. We default, I think, to 100 bytes, something like that. I can't remember what the code does. We could take a look at that. As a matter of fact, we will before we run the test. The table WCU, how much WCU do we need to allocate to the table? How much RCU? If we're creating the table, -C is the option that creates the table. The tool uses your default credentials. Whatever you have happen to running in this environment, it's going to use. If you have no credentials in the environment, it's going to fail. And then how do we optimize the keys? And this is really what we're going to talk about today, right? I mean, there's one thing, and as you start to say, okay, I just want keys 0 to 9, right? And that can work in some conditions, and in others not so well. And we're going to explore a little bit about what that means, and what does it really mean to optimize the keys. To optimize the keys, it's about getting things spread out as evenly as possible, right? If I want to minimize the number of keys that I have to use to distribute load across, I need to make sure that those keys are actually distributed on their own storage nodes, or it's not going to help me if these things start doubling up. And that's actually a condition that we're going to trap. We're going to take a look at really closely here in a second. Let's go ahead and take a look at the code we're running. It's pretty straightforward code. Again, it's an evolution of the code we've been running for a couple weeks here. We're going to come in here. We're going to initialize DynamoDB connection. We're going to parse our arguments, and then we're going to start setting some. We're going to start doing some things, right? If we want to create the table, then go ahead and do that. Create the table in the index. If -C is specified, we're going to clear any items that we had from the last run. We want an empty table to start with, because this is what I'm doing. I'm writing X number of items onto the table, and then I'm immediately table scanning the GSI, and I'm going to count the items that are in the GSI and until they're the expected number, right? Once they get to the expected number, then we're going to go ahead and say, here's how long it took, right? So that's really what this code does: load the table, scan the table, and shut down, right? The code itself to clear the table is just a simple table scan. Some of the folks are actually interested in this. How is it that you're scanning the table so quickly? How is it that you're loading items so fast? And that's really just about creating runnables, iterating on, the number of items across the item collection, and loading up these table write items, right? And then then running batches, right, to remove these items or write these items. As we look at the load item here, this is all we're really doing is we're iterating through the number of items that we're trying to insert. We're creating items, and as we start to look at the items that we're inserting, if we're generating the optimized keys, then we're creating really small items. Now, one of the ways we optimize the keys, this is the process that the way we optimize the keys is we're going to create some fake items on the table. I'm going to load a whole bunch of items onto the table that are going to, 10,000 items that are basically flood the key space. And then you're going to, when you scan the table, you're going to define some number of segments. I know I need 150 keys if I try to run 150,000 items onto the table, and I want to get it all done in 1 second, right? So if I scan the table with 10,000, if I scan a table with 10,000 keys using 150 segments, and I pick a key from each one of those segments, then I'm going to end up with a key that's on its own storage node. And that's really what the process is here when we go ahead and optimize. So there's 2 load item passes. One is for optimized keys, and the other's for the data. So if these are the donor items that we're using to optimize our keys, then we're going to use very small items. If these are the items that we're actually using to run the demo, then we're going to create those items with whatever the data blob that is specified on the command line is. Saving the items. Again, all straightforward code. The scan code is very straightforward. And then the set keys code, that defines our default keys, right? Load 10,000 donor items onto the table, scan that table with the matching the number of partitions that are specified on the command line, and get the middle result from each one of those scan segments. And then, use that and add that to a key list, and then we're going to use those, 150 keys, whatever it is that we're specifying. We're going to use those values instead of 0 to 149. If I use 0 to 149, I have no way of knowing where those keys are actually laid out, and the likelihood that they're all going to be on their own unique partition is actually pretty low, right? So, all right, so let's go and actually, run some numbers here and see what that actually looks like when we hit the table and start looking at some of these results. All right. So, so the first thing we're going to do here is I'm just going to insert 100 items into one partition. We're going to table scan that partition and see exactly what comes back, right? So this is the clearing some existing items. We can see that I deleted 100 items that would existed on the table from the previous run. That took about 722 milliseconds. It really only took that long because I had to warm up the thread pool, so to speak, right? I mean, the Java doesn't necessarily initialize all the threads when you create the pool. We loaded 100 items in 103 milliseconds, and then I went immediately scanned the GSI, and as you can see from the code, there's no, I just turn around and scan immediately. So this is a read after write verification, 100 items dumped into a single partition on the GSI, and I could not even find the replication lag. For all practical purposes, it's less than 1 millisecond in this particular example. I mean, that's really, really fast, right? I mean, that's great. We like this. Let's go ahead and look at what happens when I increase the number of items to 1,000 items. So we're going to say 1,000 items into one partition on the GSI. We're supposed to be able to write 1,000 items per second, so I would expect that there might be a little bit of replication lag in this particular case. Actually none. Again, 1,000 items in one. Now, why is that? And part of this has to do with the amount of burst capacity built up on the table and whatnot. But if I actually run that test again, you'll see the real result. And the reason why here is because in the initial pass, I only deleted 100 items, right? This pass, I had to delete 1,000 items. Well, when I delete those items from the table, it's going to replicate those deletes to the GSI. So essentially, I kind of burned down the bucket for that GSI before I even started writing items. So there was really nothing left in that 1 second that it had to work with. So it took another second for that replication to occur, right? So you're not going to see throttling on the GSI immediately, right? You're going to see replication lag increase. And that's exactly what happened here. If you look at the workflow, again, in the first workflow, we can see above, I deleted, where's my cursor? I got this giant monitor and I can never find my cursor anymore. That's all right, so the first one, I just deleted 100 items. That's 100 WCUs. I still got 900 WCUs left in that partitions bucket for that 1 second. Then I went ahead and loaded 1,000 items onto the table, and 132 milliseconds. That picks up the other 100 items that I just deleted. And so this GSI started the replication cycle essentially with an empty WCU bucket. Nothing had been consumed, so it had a full second's worth of WCU. So what did it do? It took it as fast as it possibly could, and before I could even scan the table, it had already replicated. Now in the next session, I had to delete the previous items. So I deleted those 1,000 items. It had to actually delete those from the GSIs. The GSI entered this load cycle with 0 because it loaded in 132 milliseconds, right? So as soon as I deleted, I loaded 1,000 items. It was already deleted. It was still deleting from the delete cycle. So, it had to catch up, so to speak. So during this period of time, the GSI is throttling a little bit, but not enough to cause what we call GSI back pressure and kill the table, right? If you kill the table, if the GSI backs up more than 30 seconds, right now the replication lag in this cycle is 905 milliseconds. If the GSI backs up more than 30 seconds, it's going to cause the back pressure onto the table, right? So the worst case is that your GSI replication lag could be 30 seconds, but that is absolutely gross. That's if you've just done some really, really bad things with your schema, and we're going to go ahead and demonstrate that. So let's talk about what happens if I run these 1,000 items across 10 partitions, right? So now I'm spreading that load out. I'm starting to look at, here's the items coming to the table, but as they fan out to the GSI, they're fanning out across 10 partitions. They're not all trying to slam into that one partition, right? So we can go ahead and clear those items. Aha, there we go. That's what we wanted to see, where replication lags back down to almost non-existent. Okay, so this is great. This is showing me what things could look like at scale, and or not at scale, but at least at small volume. So let's go ahead and scale this up just for one layer, and see what happens if I throw, let's say 150,000 items into the table. Okay, so I'm going to throw 150,000 items onto this table, and we're going to do it on 150 partitions, right? And I should see, that replication lag should be somewhere around 1 second based on our previous experiment. So let's go ahead and do that. Yeah, wow. That's not exactly what we would have expected, right? In my previous example, loading 1,000 items into one partition, I had, what was it? 117 milliseconds of lag? Maybe, well, no, 905 milliseconds, right? So if I went back up here, this is when I did the one partition, 1,000 items. 905 millisecond replication lag, but if I jack this up and I go to 150,000 items, it actually didn't write. I mean, the load was pretty fast, right? It was the one, I'm provisioned at 150,000 WCUs, and it loaded in 1,000 milliseconds. So that's exactly 1 second. That was, exactly what I would expect. But that fan out across the GSI was just terrible, because in this particular case, I'm using unoptimized keys, right? So if you look at the code, let's go back and take a quick look at the code. If I can actually find that section, we could take a look and see exactly what's happening as I generate these data items with unoptimized keys. Where's the code? Where's the code? Load items. Okay, so yeah, so this is the unoptimized key. And what I'm doing here is I'm just basically saying PK, GSI PK. So I've generated the PK up here. Here we go. So it's the GSI PK is going to be the, basically I'm just spraying these things across shards. This is the actual string I'm doing. It's, string, and then I'm taking the item count modulo number of partitions. So, it's evenly spreading those items out across the number of partitions. It's basically might as well be saying shard 0 to n. That's really what it is, right? It's shard 0 to 149. The number of partitions is 150. So the remainder of count modulo 150 is going to be 0 to 149, right? So, if I'm going to use optimized keys, I'm going to do what I said down below, right? Down below, when I set the keys, I'm going to go ahead and scan, I'm going to load those 10,000 donor items. I'm going to scan the table matching partitions to the segments. I'm going to go ahead and get the middle result from each scan segment, and I'm going to use those keys. So this is not going to be keys 0 to 149. They're going to be keys, God knows, shard under bar 32 and shard under bar 79, and but they're going to be spread all the way across the key space, right? Between and they're going to be evenly spread across the key space. So let's take a quick look at what happens when I do that, right? So let's go back to my storage node up here, and we can actually look at what's going on with the optimized keys. I'm sorry, I missed a question. What is the initial capacity WCU, RCU for a fresh on-demand table? I think Samane said she answered it. I'm not watching the chat, but that's basically actually that would be a question I'd have to look up. I assume it's very small, and as you grow, it has to split up. I know that customers who start with on-demand tables, the best way to start with a high capacity on-demand table is actually configure it at a provisioned throughput level that is what you think you need, right? If I need 150,000 WCUs, then go ahead and provision the table at 150,000 WCUs, and when it comes active, go ahead and turn it to on-demand. You're not going to pay for that 150,000 WCUs for more than a one billing cycle, which is a couple of seconds or a minute. I think it has to be active for a full minute before you're even billed for it. So as long as it's a process where you just basically execute the table, deployment, configuration, and then wait for active, and then as soon as it becomes active, you switch the billing mode. What ends up happening there is you're kind of forcing that table to pre-warm itself out. You're splitting out some large number of partitions, and that's going to assist in this operation, right? See, right now I had to, when I provisioned the table in the GSI, initially I had to provision those things at a high throughput level so that they would be able to sustain what I'm looking for in actual throughput. So anyways, let's get to our optimized use case. I'm going to add the -O flag. This is going to cause us to go ahead and scan the table space, find those optimized keys, and use those instead of using 0 to 149. And we can kind of take a look at what's going to happen here. I'm going to blow away those 150,000 items now, and then I'm going to load some other items. Oh my gosh, look at that. Look at that. That was amazing, right? I mean, I did this now across 150 keys, and I was able to drop that 2.3 seconds down to 0 again, uncatchable replication lag. So, if what your application really needs is read after write consistency, then DynamoDB can give you that. I mean, this proves it. I can run this test all day long. It's never going to give me a different result, right? I mean, if as long as your GSIs are properly configured to match your table throughput, and your partitioning is correctly configured, then this is going to be the process that you're going to see. Extremely low replication lag. In this example, let's take a look at what we did. We deleted 150,000 items off of the table space. We calculated those 150 well-distributed partition keys by loading the donor items onto the table. That took us 158 milliseconds. We scanned that table, again, just like almost instantaneously. It's 10,000 items on an empty table. We went ahead and calculated which keys needed to be put into the list, and the entire process to generate those keys completed in 259 milliseconds. So it's not like this takes a long time, and the only time you'd ever have to do this is when you actually onboard the customer or the seller, right? How much capacity do you need, Mr. Customer? Okay, let me generate your keys, and then you can store that key list on the customer's data object, so that when you load whatever process it is that's bulk loading the customer's data, you know which keys to use. This is going to give you the ability to use a small number of keys to distribute that load. Now, the alternative would be to say, okay, well, I don't want to optimize. I don't want to do any of that. Let me see, how many partitions do I need? Okay, so 150,000 items, 150 partitions. We saw that result. We can look at it again. Go ahead, clear those items from the table that we just had. Load some items. Read. Eventually, we're going to come up with an answer. It says, okay, 2.3 seconds. Let's double the number of partitions and see what it takes, right? Maybe instead of 150, let's use 300, right? So now we've got, theoretically, I've got twice the number of partitions that I got on the table. So, but it's still, geez, in this case, just bad, right? Why? Because I'm hammering the GSI in the table now multiple times, right? I just hammered that previous run with, it took 2.3 seconds, but I'm burning down the reserve capacity of the table and the GSI, and eventually it's going to get down to my provision throughput, and that's going to be limited by the number of partitions that we actually have on the table. And I'm also competing. Remember, this scan is running on the GSI. It's just hammering it. It's coming back and back and back and back. So it's actually competing for IOPS with the updates from the replication. So you're going to get really inconsistent results. I doubled that. Let's go to 600 and see what happens. Right, and what we're seeing right now is just the facts of life when you're dealing with binomial distributions and hash algorithms, right? I mean, okay, so even at 600, not a noticeable difference. I mean, at some point we will get to a noticeable improvement, right? I think that's that point somewhere around 3,000 or 6,000. We're going to get to the point where this thing's going to start to behave in a way that we like to see. Hey, there we go. We're actually starting to get better, right? With the throughput. But as you can see, look, the number of partitions that I have to use to be able to spread that data out, to be able to get it to more efficiently scale. I mean, whoa. I mean, go through the options of just, saying, okay, I know I need 150,000 WCUs. I need 150 optimized keys. Let me go ahead and generate those keys. And this gives me the ability to execute at a much, much faster pace. Right. I mean, it's just, okay, there we go. In the first pass, we actually caught it. It was 27 items out of the 150,000. Did not replicate fast enough for me to catch in the first scan. So I had to actually scan it 2 times in order to get 150,000. You see how fast it's actually replicating. The replication lag says 200 milliseconds because, well, yeah, technically it was. I went through one scan at 200 milliseconds, but if I had waited, another millisecond, I wouldn't have had to make the second scan. So I could probably deduct 100 milliseconds from that and say that was my real replication lag, was like 100 milliseconds, because it took me 100 milliseconds to scan the table. So these are the kinds of things that we're going to go through to optimize your deployments, to make sure that your keys are sharded correctly. We can run these types of exercises on the table itself. We can run these types of key generations for GSIs and indexes. And one of the things that was interesting as I went through the exercise, I wanted to verify that if I scanned a table in my account space and got these results, did those results apply to the other tables in my account space? And the answer was yes. I don't necessarily need to have a donor table that's the exact same table that I'm loading data onto, because that would be problematic as you start to bring new customers on board. You've got data on the table. So, how are you going to, I mean, your scans are going to just take longer and longer, right? So, but this way, what you can do is you can just have a little pocket table over there on the side that you use to generate these keys. You can run this little process that scans across that table space. And the one thing that I didn't address in this implementation is that you need to remember is that the first and the last keys are always going to be on the same storage node. So even if I have 1,000 nodes on my table, if I run this particular algorithm, every customer is going to have one partition on the first node and one partition on the last node of your key space. So if you actually want to do this in production and you're going to be signing up a whole bunch of customers or running at real high velocity, and one of the things we're probably going to do for the mortgage customer I was talking about earlier is we're going to generate a little bit different algorithm than just a straightforward linear distribution from end to end. Maybe throw in some sort of a offset or some sort of a random offset when I onboard a customer, because if I'm using like a customer ID as a prefix to the partition key, then that's going to cause distribution across the storage nodes right there, because the hash code from one string is not going to be equal to the hash code of the other. But again, the first node is always the first node. The last node is always the last node. So having some sort of an offset or a random offset kind of gives you a better idea of how to guarantee random distribution of your customers across those shards. In this particular example, it was kind of the extreme example. My table's provisioned at 150,000 WCUs, and what I'm showing you is 150,000 WCUs worth of replication throughput at a very, very low replication lag, right? So, this is the key here, is that to understand that, at DynamoDB, it's all about how we set the schema. It's going to generate the kind of performance that you're going to experience in your application. So that's what I've got for you today. Hopefully this was an informative session. It was certainly informative for me as I dug through all of this and started to get down into the recommendations. I mean, in the past, it's been easy to just tell people, you need 25,000 WCUs, use 0 to 24. But, hey, in the reality of it, then this is, and I actually owe some customers an apology, because some customers have come to me in the past and said, hey, Rick, we're seeing replication lag that's, higher than 1 second. And I'm thinking, well, that must mean that you have key pressure and GSI throttling. And they're like, no, we have no write throttling. And, but actually now, having dug my hands into this and digging deep into the way these things work, not just with this customer recently, but with customers since I've talked to, had those discussions, it became obvious that, it's that random distribution of, hashed values is not necessarily going to be even unless you increase the number of samples, right? And that's really what these, like an MD5 hash algorithm, when you go look at it, it even tells you that. It's evenly distributed, but that's not guaranteed across a small sample. And so if you're just like generating 25 keys, then the likelihood that a couple of those keys could land on the same storage node is fairly high if I have a smaller number of storage nodes. Now, if I have thousands of storage nodes, then sure, I could just go 0 to 24, not a problem. But again, if I'm not distributed out, my table's not spread out that far, and the number of partitions I need to exercise is closer to a meaningful percentage of the partitions that I have on the table, then this is going to be a much better pattern for you. So anyways, that's what I got for you. Hopefully that was informative. If there's any questions that you guys want me to talk about, fire away. I'll give the moderators a few minutes to collect and get that information back to me, and we'll go from there. Any questions? Did I put you all to sleep? Or maybe my moderators are just so good they answered all the questions already. All right, well, hopefully one of these days you guys will get more interactive with me. I do see that we get a lot of views on the videos, and I love it. Thanks, guys. It's really nice. And, again, next week what I'm going to do is I'm going to get back to data modeling. We're going to go, and I haven't picked the model yet, but I'm going to pick another application that's going to be, maybe... I don't know yet, but I'll tweet about that on Sunday or Monday, and we're just going to go ahead and do another straight modeling session. I know some people have been asking for more of that, so we'll get into that next week. And the week after that, we're going to have a really good session. I'm going to bring one of our serverless gurus on board. We're going to do a session where we're going to demonstrate the Lambda direct resolvers for AWS Amplify and how to use single table design with AWS Amplify implementations, and this has been a big question from the Amplify community: is how do we resolve this? We're going to actually do that, and now that we have direct Lambda resolvers, it makes it easier for us to do that. And so that's going to be coming in 2 weeks. Again, next week we'll work on a data modeling session. I'll let that information out later on this weekend. I'm going to go ahead and pick that model. And thanks so much, everybody. I really appreciate your time, and have a good day. Take care of yourselves.